We have seen that Faraday's law says that the induced electromagnetic force in a closed loop is proportional to the rate of change of the magnetic flux inside this loop. And when we have write it in a numerical form, we said that EMF equal minus partial phi d by partial t. And we said that this minus would be due to Lenz's law. So we are going to discuss what is Lenz's law. Lenz's law states that the introduced current has a direction that the magnetic field due to the current opposes or in the opposite direction to the change of the magnetic flux that induces this current. What does this mean? It means that if I have a magnet bar like this, and this magnet bar has this north side and this south side, and I'm forcing this magnet bar to go inside the loop. So this magnet bar is increasing the north inside the loop. Now the induced current inside the loop will make the loop as a magnetic dipole, which is equivalent to a magnet, and the direction of this magnet is opposite to the direction of the coming magnet bar. So in this case, I am pushing the north from up to down. So there is a north is coming from down to up, which is opposite the direction of the magnet bar. So that's what Lenz say. An induced current has direction such that the magnetic field due to the current, opposes in the opposite direction, opposes the change of the magnetic flux. So if the magnetic flux increasing north, so it is opposes the north, so it would be in the negative side. So north coming from top to bottom here, it is coming from bottom to top here. But in the case that the magnet is already inside the loop, and I'm trying to moving the magnet from the loop, so opposites here would be in the negative side. So that's what we are seeing. As the magnet is moved towards the loop, a current is induced in the loop. The current produces its own magnetic field with magnetic dipole moment mu oriented so as to oppose the motion of the magnet. Thus the induced current in this case must be counterclockwise, such that it's north in the up. Now, if we next pull the magnet now is inside the loop and we are going to pull the magnet. If we next pull the magnet away from the loop, a current will again induce in the loop. Now, however, the loop will have south pole facing the retreating north pole of the magnet. So in this case, when I'm moving out the north, there will be north on the lower side due to the magnetic loop. So it opposes the motion of the magnet outside or out of the loop. So in this case, the north of the magnetic dipole moment of the loop would be down and the south would be up. So according to the right hand rule, the current in this case would be clockwise. It would be coming in this direction. So in general, the current will introduce magnetic field opposes to the pole movement or in the opposite to the pole movement, regardless it is coming toward or outside the loop. opposition to flux change, assuming that we have the original magnetic field B in this direction and it was small. Then after a while it has been increased. So the induced magnetic field would be opposite in opposite direction, and as long as the original magnetic field is increasing, the induced magnetic field would be increasing in the opposite direction. So if the original magnetic field is increasing from top to up, from down to up, the induced magnetic field would be going in the down direction. So according to the right hand rule, the current would be clockwise. Now, if we are assuming that we have the original magnetic field B at the initial time was like this, and after a while has been reduced to this value. So the magnetic field in this case is reducing, not increasing. If the original magnetic field is reducing, the induced magnetic field would be increasing to be opposition. This is decreasing in the original of the magnetic field. So in this case, the induced magnetic field will be increasing in the same direction of the original magnetic field, which is decreasing. So in this case, the induced magnetic field would be in this direction, and according to the right hand rule, the current would be counterclockwise. That's what we are seeing. The flux of B induced always opposes the change in the flux B. But B induced is not always in opposite of B. If the external flux is increasing in one direction, then the induced flux would be opposite to the external flux. But if the external flux is decreasing, not increasing, in one direction, then the induced flux would be in the same direction of the external flux. And that's what we are seeing, increasing the external magnetic field induces current with field B induced that opposes, that change, that in the opposite direction. Now, decreasing the external field B induces a current with a field B induced that opposes the change too. But now, because I'm decreasing the external magnetic field, the opposition here is increasing the induced field in the same direction of the field. As an example, the figure here shows a conducting loop consisting of a half circle of radius r equals 0.2 meters and three straight sections, this straight section, this straight section, and this straight section. The half circle lies in a uniform magnetic field B. Only the part of the half cycle lies in a magnetic field B. That is directed out of the page. So the direction of the magnetic field is coming from the screen towards your eyes. The field magnitude, the field B magnitude is given by B equals 4 times t squared plus 2 times t plus 3. So it is time varying field. And according to these values, as t is increasing, the magnetic field is increasing. So it is time varying and it is increasing magnetic field. With B in Tesla and T in seconds. So the units are the SI units. Now an ideal battery with EMF battery equal 2 volts is connected to the loop. Here is a battery with 2 volts connected to the loop. And the resistance of the loop is 2 ohms. The resistance of the complete loop is 2 ohms. Okay. Now it is required. What are the magnitude and direction of the EMF induced around the loop by the magnetic field at time t equals 10 seconds. It is required to find out the induced electromagnetic force due to the changing of the magnetic field inside the loop at time t equal 10 seconds. Okay. As we mentioned, the induced electromagnetic force equals the rate of change of the magnetic flux with respect to the time. The magnetic flux equals the magnetic field multiplied by the area of the loop inside the magnetic field. In this case, the area of the loop inside the magnetic field is only this half circle. This part, this straight part, is outside the magnetic field, as it is seen. The magnetic field lies only on this half circle. So, the induced electromagnetic force would be dBA over dt. And because the area is constant with respect to the time, so we can get the area outside the differentiation. So in this case, the induced electromagnetic force would be the area multiplied by dB over dt. And actually we have B as a function of t. So we can differentiate this one with respect to the time. The area is the area of the half circle. The area of the circle is pi r squared. So this is half pi r squared. Okay. So by applying all these parts, we see that the induced electromagnetic force would be the area multiplied by dB over dt. It would be the area half by r squared, half because it is half a circle. dB by dt equals d over dt, and the value of b 4t squared plus 2t plus 4, plus 3. So now by taking the differentiation of this equation, we find out the differentiation of t squared is 2t, so it is 8t. The differentiation of t would be 1, so it is 2. The differentiation of the constant would be 0. So this is the differentiation of b with respect to time. Now, by applying the radius to be 0.2 meters, so pi multiplied by 0.2 meters squared over 2 multiplied by 8t, and we want to find at t equals 10 seconds, so 8 multiplied by 10 plus 2, we can find out the induced electromagnetic force due to the changing of the magnetic field inside it. So the induced electromagnetic force in this case would be 5.152 volts. This is the magnitude. Now it is required to find out the direction. What is the direction of this induced electromagnetic force? Find out the direction. We say that the flux is increasing and it is coming outside of the page or outside of the screen. So the induced electromagnetic force will introduce a current which introduces magnetic field opposes the change of the original magnetic field. So if the magnetic field is increasing to be outside of the screen, so the induced magnetic force or the induced current will introduce magnetic field which is inside the screen. So according to the right hand rule, the current will be following in clockwise. The current would be following in clockwise. So to find the direction of the induced electromagnetic force, we first note that the flux through the loop is out of the page and is increasing because the induced field P induced due to the induced current must obey that increase. It must go into the page. So using curl straight line hand rule, we find the induced current is in clockwise around the loop and thus also the induced electromagnetic force. So it is coming in this direction. Effectively, if it is incoming in this direction, it is in the opposite to the electromagnetic force of the battery. Right? Because the battery will introduce current coming counterclockwise. But the induced electromagnetic force due to the change of the magnetic field, in this case, is clockwise, so it is in the opposite to the battery. Part B of the question is, what is the current in the loop at time equal 10 seconds? Effectively, the current at the time 10 equal second would equal the total electromagnetic force inside this loop over its resistance. And in this case, we have the induced electromagnetic force equals 5.152 volts, which is nearly 5.2 volts, for example. And its direction, as we mentioned, in the opposite to the direction of the electromagnetic force of the battery. So actually they subtract from each other. So the total electromagnetic force in this case would equal the induced electromagnetic force minus the electromagnetic force of the battery. So the net electromagnetic force equals induced electromagnetic force minus the electromagnetic force of the battery. If we divided the net electromagnetic force over the resistance, we can obtain the current. So the current would be 5.152 volts, which is the induced electromagnetic force, minus 2 volts, which is the electromagnetic force of the battery, over 2 ohms, which is the resistance of the loop. So we can find the current in the loop at the time 10 equals 10 seconds equals 1.58 ampere. Okay. And the direction of the current would be in clockwise. Alright.